volunteer from Shiv Shankar. Shiv Shankar, are you there?
Yes, sir.
Okay. Are you ready now?
Good afternoon, sir.
Good afternoon. Okay, so sharp at 2:30, you have to start introducing the speaker, right?
Yes, sir. Yes, sir.
बाकी सुबह सर वहाँ पे आगरा में कैसे हैं सारे लोग?
हाँ सर, ठीक है, सारे लोग ठीक है।
ओके, कोरोना का इम्पैक्ट तो अब कम हो गया होगा आई थिंक।
हाँ, बहुत कम है, पहले ज्यादा था।
ओके। हेलो जितेंद्र सर।
हेलो, नमस्कार शुभो सर। और
नमस्कार सर।
सर पहचान लिया ना आपने या भूले नहीं?
अरे आपको कैसे भूलेंगे। और सब बढ़िया, सब ठीक है ना? एवरीथिंग इज
हाँ सर, हाँ सर सब ठीक है, आप बताइए।
हाँ, यहाँ भी सब ठीक है।
अच्छा है सर, सो थैंक यू सर।
थैंक यू सर।
आई थिंक 2:30 ना?
It's 2:30, so I request Shiv Shankar to introduce the speaker. Shiv Shankar.
Yeah. Hello. Good afternoon to all. Hope all are good in this pandemic. I am Shiv Shankar from NIT Jamshedpur. Welcome to the online short-term course on recent trends in microgrid, that is RTM 2020. We now have expert talk 8 to be delivered by Dr. Subho Upadhyay sir, Assistant Professor in the Department of Electrical Engineering at Diyalbagh Education Institute, Agra. Dr. Subho Upadhyay sir has obtained his BTech degree in 2010 from Dr. APJ Abdul Kalam Technical University, Lucknow, and MTech degree in 2010 from Birla Institute of Technology, Mishra, Ranchi, Jharkhand. Sir has received his PhD degree from IIT Roorkee in 2017. His interests include solar PV system, hybrid energy system, microgrid control, and automated traffic light controller. Now I would like sir to take session and enlighten us. Dr. Subho Upadhyay sir, please.
Okay, thank you all. A very good afternoon to all the faculty members, dear students, and the researchers. So can I start presenting?
Sure sir, sure, please sir.
Okay. Thank you. So is it visible to all?
Not yet. Maybe it will take some time, I think.
Okay. Now is it visible?
No sir, no.
Yes, it's coming now.
Okay. So thank you. A very good afternoon to the faculty members, researchers, and dear students. So I would like to thank the organizing committee of NIT Jamshedpur for giving me an opportunity as a speaker to deliver a lecture on the short-term course, that is recent trends in microgrid 2020. The topic of my presentation is based on design of power distribution network in hilly area. Why this topic is important? So it is important because through these recent years, we have seen a drastic change in increase in the development of microgrid and distributed energy systems, which has resulted in a large, which has increased the advantages, that is the environmental emissions due to use of renewable energies as the sources for developing the microgrids has reduced the emission level. It has also given an ample opportunity to the local people living in rural areas as job creations. Not only that, it has also provided a daily and continuous flow of electricity at a genuine charge. So keeping these important features and important advantages, it is important to design a power distribution network. So the topics that I will cover during this lecture is a case study. In that case study, a sizing methodology will be followed. With the help of sizing methodology, we will obtain some sizes of different generators that are needed to be placed in a digital elevation map of the area which is located in hilly region. Since the region is hilly, so we have to place these generators according to the resource assessment and load requirements. And since this is a hilly terrain, so we have to find out the shortest path so as to design the distribution network in the hilly area. Finally, there will be load flow analysis for selection of conductors, and after the selection of conductors, it is based on the voltage drop as well as the power loss calculations, on the basis of which we will obtain the COE of the conductor cost, hybrid energy system cost, and also we will include the cost saved due to not using diesel generators in the overall cost of energy of this system. And finally, we will draw some conclusions from it. So a brief idea about the sizing of the system components. Firstly, there are multiple state nodal agencies such as UREDA and UPCL, from which we will be able to understand, we will get the data about the important features of the villages which are unelectrified or electrified to a limited extent. So according to the different villages, we will cluster them in a proper manner so as to get an ample amount of load which will be around some kilowatt or megawatt range, so as to fit an integrated renewable energy system or hybrid energy system. Otherwise, more than one sources would not be required in such cases. So to make it much more understandable and to increase the complexity of the problem, we needed to increase the amount of demand requirement. So after determining the demand requirement, we have to distribute it into hourly basis. Since the demand is in kilowatt, so the locally available resources such as solar radiation, hydro head discharge, biomass availability, and cattle dung required are being again converted into kilowatt unit with the help of mathematical modeling of the system components. And then we have to select the configuration, that the configuration can be AC, DC, or can be DC. So there are multiple configurations available. We have to choose among them. Then we have to make the power balance equation, which is the balance between demand and resource. And this balance need to be fulfilled at all times. That means the reliability in this case will be unity. So there is an energy management system which keep in mind whenever the renewable energy resources are unable to satisfy the demand, in such conditions, we should use batteries which will charge, which will be charged whenever the resources, whenever the energy or the power delivered by the sources will be much more than the demand. Then we can charge the batteries and we can derive the power from the batteries whenever the demand is more. Even there may be some conditions where diesel generators is required to supply the net demand, as the batteries, the SOC state of charge of the batteries can be less than 20%. In such conditions, diesel generator along with the batteries can be utilized in multiple ways, which is dispatch strategies or power dispatch strategies for supplying the demand. So again, after designing the system, it is important to finalize the objective function and the constraints. So according to the designer, according to the researchers, they have the opportunity to decide what may be the objectives. The objective of the problem can be cost, can be reliability, can be environmental emission, land requirement for installing solar SPV, their job creation. There may be multiple factors that can be considered for designing the system. Finally, we will optimize this problem for determining the SPV, solar photovoltaic system, the size of SPV, diesel generator and batteries can be obtained using different optimization techniques. Finally, we will get the cost of energy of hybrid energy system comprising of different generators along with diesel generator and battery bank. Not only this, we will also get the maintenance cost, maintenance and operation cost and replacement cost for 25 hours of 25 years. So the case study, after utilizing this sizing methodology, the size of different generators were calculated. That is MHP, that is hydropower, micro hydropower of 15 kilowatt was present nearby the site. 2 biomass gasifiers of 15 kilowatt was calculated. Similarly, 3 biogas generators along with 1 biogas generator of 10 kilowatt and 5 kilowatt each. So in this condition, we have obtained that the peak demand is 102 kilowatt. Peak was available. Similarly, different sizes of interfacing devices, power electronics devices were also obtained. So now we will focus about how to design the system, overall distribution energy system. So we will look into a figure consisting of 3-dimension view, that is consisting of latitude, longitude and elevation. In this figure, there are 7 villages. These 7 villages comprises of different latitude, longitude values along with the elevation. We can directly see, we cannot draw the distribution network directly because the terrain is uneven. So in this case, how to make the connectivity possible? How to design a system where the distance between consecutive nodes or distance between source and destination will be minimum. So how to calculate it? So we can change this 3D platform into 2D platform. If we change this 3D platform into 2D platform, we can get a characteristics graph between distance in the y-axis and distance in the x-axis, representing the latitudes and longitudes. With the help of this, we can get the x-y coordinate values for each load centers and generating centers. Here load centers are the villages. So according to the barycenter formula, we will understand how to obtain the generating center. So we know that the biomass and biogas generators along with the hydropower sites cannot be changed, since biogas accumulation and biomass accumulation are limited to nearby area, nearby to the villages. The village which provide maximum amount of biomass comprise of particular kilowatt capacity of generators. So we can see that Naugao village around 15 kilowatt of biomass gasifier and biogas generator of 10 kilowatt can be placed. That means 15 kilowatt of biomass is available in that site and 10 kilowatt of cattle dung is available in that locality so as to supply the generator. But the problem is that how to place the generating center comprising of diesel generator, SPV, battery bank, power conditioning devices. So how to place this generating center, that can be calculated using barycenter formula, which is nothing but the product of the power comprising of a particular village multiplied with the coordinate that we had already discussed, that is the coordinate comprising of x and y axis of a particular village. So using this formula we can obtain the generating center coordinates which is given here. So in this condition we are considering the load as at maximum value. The load from 9 p.m. to 10 p.m. was considered to be maximum, which was coming around 102 kilowatt. So according to that we have to supply the demand. So now our problem is switched to find out the shortest distance for designing the distribution network. So to do so, we have to minimize the distance, total distance between source and destination centers. So there are 9 nodes, 7 villages, 1 hydropower center, and 1 is the generating center. So there are 9 centers. We have to find out the minimum distance between the consecutive centers. So how to obtain that? By taking the summation of the intermediate node, that is the minimum length between depends on the sum of the lengths between all the intermediate nodes, that is Ni and Nj, while A is the intermediate section. So here we can see LSD where S is the source and D is the destination. The total distance between a source and a destination can be calculated as the summation of Lij, where Lij is the distance between 2 consecutive nodes and A is the sectional distance. So for simplicity, let us take 2 centers. Another is a village load center, that is Sirani village is there. So we have to find out the distance between the generating center and the Sirani village. So there is a way to calculate it. Here we can find out that there are multiple number of latitudes and longitudes are present. So in the second diagram we can see in the step 2, initialize intermediate nodes. Here we can see if we place the source node and destination node to a latitude and longitude values, then we can see we can move these nodes according to the latitudes. Here we can see the number of longitudes are more than the number of latitudes. So here how we are able to calculate the distance is the number of longitudes will represent the number of nodes. Here since the number of longitudes are more, so the number of nodes will be equal to the number of longitudes, and the nodes are being moved in the latitudinal direction. So here if we see there are 15 longitudes, so there will be 15 nodes, and the optimization of the distance can be found out by moving these nodes in the latitudinal direction. Since there are, let us consider here 4 latitudes, so there are 4 possibilities for node 1 to move similarly we can move the corresponding nodes. So the distance now, at step 3 we will find the distance between intermediate nodes. So how to find the distance between intermediate nodes? It can be calculated as the Euclidean distance, because there is an elevation point of view is coming. So we have to consider the elevation part, that is Euclidean distance. Okay, so by taking the summation of intermediate nodes, we will get the total distance, that is LSD. LSD equal to summation of A is equal to 1 to A is equal to M I L I J. So we will, from this we will able to obtain the distance between two consecutive source and destination centers. Again, in step 4, after obtaining the LSD values for each section, we can make a summation of these sectional distances and we can obtain the overall distribution distance. So where TD is the total distance. So after applying the biogeography optimization technique, we would able to obtain the characteristics, which the graph number 1. So here graph 1 is represents the distance between two consecutive nodes or two consecutive source and destination centers. So here Nagaon and Junar are two villages. So we can optimize this distance, which is represented in graph 1. Here in the left side is mentioned in meters. So we can see that it is, if we convert it into kilometer, it will be 5, 6, 7 kilometers. So by making a summation of all these iterative values, we can obtain the graph number 2, which is visible at the lower portion. The graph number 2 represents the summation of all the distances. So again, if we compare this with Dijkstra algorithm, which is another important algorithm in computational technique, if we apply it, then we will able to see that using BBO we will be able to get a total distance around 16.05 kilometers. So here we can clearly see the distance between two important source and destination centers, which are given in this table. So the total distribution network distance calculated using Dijkstra algorithm is 18.8 kilometer, and using BBO it is around 16.05 kilometer. So after representing these distances in the DEM, digital elevation map, we will get these characteristics, and the pink line is showing us the distance between two consecutive nodes, that is source and destination centers. So after obtaining the consecutive distances, we can have the single line diagram of these 7 buses, which are load bus and generating center bus number 1, and bus number 7 is the hydro center. So if we apply the load flow analysis, then we will obtain the power loss. Before going into that, firstly there are multiple numbers, different numbers of ACSR conductor, which is aluminum conduit steel reinforced conductor. So there are multiple different number of conductors available in the market, whose data is being provided by reference number 7, where we will get the series impedance value, cross-sectional area of different conductors, and the weight per kg per kilometer distance. So, and also considering the power loss equation, that is I square R losses, we can, after applying the load flow analysis, which is Newton Raphson in this case, we can obtain the voltage per unit drop at each bus. So here in this case we can see, if we move from Wesel to Leopard, then the weight is increasing and cross-sectional area is increasing. That means the cost will also increase. That means if we move from Wesel to Leopard, our cost as well as cross-sectional area and weight will increase. But the problem is that we have to reduce the cost. we have to for reducing the cost, we have to apply certain conditions. So in this condition, we can consider a per unit drop of 0.9. If we can see that at bus number 9 and bus number 4, the voltage drop is maximum. So if we consider this mean conductor, which is shown here in blue line and green dot, it can be seen that this, if we select this conductor, the per unit value is at bus number 9 is more than 0.9, so we can select this. If we select the rabbit conductor, we can see the per unit drop at the bus number 9 is more than 0.9. So we will apply certain conditions. Now, after applying the load flow analysis, we can get certain results, which is there are rupees per kilometer cost are being available in the reference 8. With the help of that, we will get some power losses. Here, if we select the mean conductor, we will get the power loss of 5 kilowatt. So we have to keep in mind the 5 kilowatt loss also. And here in this case, the cost of implementing the ACSR mean conductor for this system will be around 1 crore rupees, over 1 crore rupees. If we multiply this INR per kilometer rate with the total distance, that is 16.05, we will get the overall cost for implementing distribution system. So finally, again, as we have considered the diesel generator also, so diesel generator will emit emissions, that is CO2 in this case. So cost for not using diesel generator can be calculated as cost saved, which is given according to United Nations. It is given around $11 per ton of CO2 not emitted. So it can be calculated as WED. Here WED is the way, if we use only diesel generator for supplying this demand, what will be the total emission that is given by WED, whereas WEDS is the total emission in the present condition. So it is actually emission that is in kg per kilowatt hour of diesel generator use. WEDS or WED is given in kg per kilowatt hour. So if we have to multiply it with 660 is nothing but $60 is the unit change with rupees, and $11 per ton is being given as United Nations data, and N is the total number of years of operation. So with the help of this, we can get CS. Here WEDS is the total amount of CO2 emitted by the diesel generator present in the integrated hybrid energy system. Okay, so finally, the cost of energy, if we consider only the hybrid energy system implementation, maintenance and replacement cost of different generators and power conditioning devices, and if we select the different dispatch strategy is basically the way of utilizing batteries and diesel generator for supplying the net demand. So if we select the cycle charging strategy, the cost of energy is 5.64 compared to load following and peak saving strategies. So if we select different type of strategies, we can get different COE. This COE is basically calculated without considering the conductor cost and cost saved due to not emitting CO2. So again, if we consider COE with conductor cost, the cost of energy will increase. And finally, if we consider the CO2 emission cost saved, then the rupees per kilowatt hour will reduce, which can be calculated using this formula, which is COET is CCT, which is cost for implementing distribution system, plus TNPC, which is total net present cost, minus CS, which is cost saved due to not using diesel generator, into CRF, which is capital recovery factor. It is a capital recovery factor which is based on the discount rate divided by the summation of total energy supplied over an year by all the generating systems. So if we get into the sensitivity issues, that is sensitivity analysis, then we can see that if we see that if we use cycle charging strategy, then for the third case we can see COE with conductor cost and cost saved from CO2 emission is around 6.32 rupees per kilowatt hour. If we consider this to be the exact value or the present condition, then it is represented by the middle line. And if we decrease, if for any instance or any condition the rate, there is a reduction in the diesel fuel price around 10%, or there is a reduction in the demand, or there is an increase in solar radiation, will overall decrease the COE, whereas an increase in diesel generating cost, diesel fuel cost, an increase in demand and decrease in solar radiation will increase the cost of energy. So from this we can draw certain important conclusions, which is we can develop the digital elevation map of the area using ArcGIS, and we can implement the different generating centers, and with the help of that we can calculate the shortest distance using Euclidean distance, using BBO and DA techniques. And finally we have evaluated that the cost of the kilometer coming out using BBO is around 16.05 kilometer, whereas by utilizing DA it is around 18.8 kilometer. Finally we have drawn the single line diagram, and by implementing the load flow analysis we can obtain an overall COE around 6.32 rupees per kilowatt hour if we consider the total net present cost plus conductor cost plus cost saved due to not using diesel generator. So we have discussed about there are three different strategies. If we consider the cycle charging strategy, how it is implemented. Actually, cycle charging strategy is a way where initially the load is being supplied by the renewable generators. If the renewable generators are unable to supply the demand, batteries are being utilized to supply the demand. And if batteries are supplying and its SOC has reduced much more than 20%, then we have to utilize the diesel generator, which will work in two front, as to supply the net demand and also to supply the and also to charge the batteries with the help of remaining power which is not supplied to the demand. Similarly, in case of load following, we can see it is a way whereas renewable energy is supplying the demand which is given as the preference, and if renewable energy generators are unable to supply the demand, in such conditions batteries are being utilized, and if batteries are unable to supply, then diesel generator is used to only to supply the demand. It is not charging the batteries. Whereas in peak saving, we can see in peak saving, after utilizing the renewable energy generators, we can use diesel generators instead of batteries to supply the demand. If the diesel generators are unable to supply the demand, then batteries are utilized to supply the saved peak saving amount of energy, the remaining amount of power which is required. So we can see there are multiple advantages of using cycle charging strategy. That's why cycle charging, the COE for cycle charging strategy is minimum in this case. And finally, we have obtained that if we reduce the solar radiation, increase the demand and increase the diesel fuel price, there is an increase in cost of energy. And simultaneously, there will be decrease with the increase in solar radiation, reduction in demand and reduction in diesel fuel price. These are some of the important references that I have utilized. Here you can find that UNFCCC. Here I have obtained the $11 value per ton of CO2 emitted. Similarly, different important references are there. Okay, thank you. Thank you.
Thank you so much, sir, for such a lovely presentation. And the session is now open for questions if there is any. Any question from the participants? You can also type into the chat box. Let us wait for a minute or two if somebody is having a question.
Hello, sir.
Yes.
Yes, please.
Sir, is your work confined only to finding the placement of DGs and drawing the single line diagram, or you also have worked on what is the cost of each DG, how it has to be in the pricing methodology? Any?
Okay. I've got your question. Actually, there are two parts to the problem, to solve this problem. Firstly is to size the different generators. I have not covered in this session. I have not covered the sizing portion, which is the sizing of different generators, which is basically based on the suppliers. According to the suppliers data, we can obtain the cost of different generators, and we can obtain these generators according to the resource as well as load requirement. And the main motive of this presentation was based on finding the shortest path. So a new algorithm was developed for that.
Okay, thank you, sir. Sir, one more doubt. You said you have used the load flow analysis, right? How is this DGs? They have been modeled for load flow analysis.
Actually,
have they been modeled as a constant source or some varying source? How they have been considered into the load flow analysis?
For load flow analysis, I have considered the hour where maximum demand is there. So the hour that is from 9 to 10, I have considered a constant demand and constant sources for that particular hour.
Okay, so the energy power demand, power generation from the DGs we have taken as constant, is static at that particular instant of
time. But it will be much more beneficial if we cover the variability that is for each hour. If we determine the load flow analysis, it will be much more clearer.
Okay, so thank you very much.
Sir, good afternoon, sir. This is Dr. Sharmila from Anna University, sir.
Yes.
I have got a good experience about your institute, sir, Dayalbagh Institute, because we had worked Anna University along with Dayalbagh, sir. I heard that you have some microgrids, like a distributed generation long back, sir.
Yes.
If that is the reason, if you can integrate the real-time system into your algorithm, sir, how can you do it, sir? Like, because you have very good solar and kind of a system available which is running and feeding the what do you call your solar powered vehicle and all those things. How you can model them in a real time, sir? If you have a real system, because in Anand also we have got some nearly 20 kilowatt capacity, sir. If that is all in distributed manner only, what are the things to be taken in modeling with a real time system, sir? Do you need to model in your same algorithm, or can you use a ETAP, sir, for modeling?
ETAP can be used for determining the loss analysis and placement of generators can be found out using ETAP. And for obtaining the real-time simulation, we can design the system in real-time simulators such as OpenRT, and there are multiple platforms are there where we can model the system, and we can run these machines in real time.
What are the things to be done, sir? Like you have developed this algorithm. If I want to incorporate the real-time system, what kind of things I have to take into account, sir?
So for real time, we have to firstly consider the variability of the loads. That is, there must be load. Without load, we cannot supply the generation. We cannot have the generation. So we have to take into consideration different loads. So in case of OpenRT, or you can see the real-time simulators are there. Firstly, we will incorporate these models in the real-time simulators. It will benefit us in a multiple ways. So we can design this algorithm in different platforms, but for checking it into real time, there are multiple loads available. In case of, if you look into different catalogs of OpenRT or different type of simulators are there, they are providing different type of loads, which you can see that they can be seen as somewhat work in the real time. Okay, we have the real time experience if we operate these different type of loads provided by different type of means.
Okay, sir.
Okay,
Thank you, sir.
okay, you have
Thank you.
We have worked like Sendil one from E&I department. We had interactions. Sir.
okay.
We adopted a village in Tirunelveli, sir. That time Dayalbag was a major kind of resource person, sir, in our venture. Some 3 to 4 years before, sir.
Okay, sir.
They were forwarding the solar mission, sir. Actually, solar mission policy. That's it.
Okay.
Thank you very much, sir.
Thank you.
Thank you, Dr. Shavila. I think that was a nice question and nicely answered, I think. Sir, if you can see, there are 2 more questions in the chat box. If you are able to open it. One from the first question is how the control parameters of the BBO algorithm are selected for the sizing problem.
Okay. Okay. So it is a very important question, an interesting question. Actually, BBO works on the way of immigration and migration process. Whenever whenever we optimize the problem, whenever we apply the optimization technique, there is a buffer. So in buffer, we will order these different type of solutions in a way where minimum cost, or we can have the minimum value at the first element of the buffer and maximum as the last element of the buffer. So we can consider the crossover point. There is a crossover point. We can, with the help of that, we can change the number of elements will be present in the buffer for the next iteration. That means if there are 10 elements in the buffer, we can consider only 5 elements for the next iteration, and we can delete the remaining 5 elements. So we have the possibility to control the size of the buffer, as well as we can change the parameter which is selecting these different type of, means it is basically, as well as there is a mutation probability is there. So there are 2 ways to change the way where BBO is working. So first is that there is a crossover point which is selecting the buffer size, and there is a mutation probability which is changing the variable for each iteration. And second is that why load is maximum at the 21st hour. It is because there is a summer load, or whenever there is a summer load, at the night time from 9 to 10, I've considered in the problem that some of the shops are closing at the night, okay, around 10 o'clock, or a pump is also being operated at that time. That is water pump. So since water pump is working at that time as well as fan loads are there, that's why the load is maximum in that time. And TVs as well as people are waking up to 10 p.m. That's why the load is maximum at that time. But you can change it according to your perception, because these areas are not electrified, so you can have your own choice about the maximum demand, where it will lie.
Yes.
Thank you.
Apart from this, I can also add to this. There is, I think, biomass-based generation as well, right, sir?
Yes, yes.
At Dalbagh Educational Institute, no?
Yes.
Yes. So if somebody is interested, then he may connect and send his queries or her query directly to the Dr. Subho Upadhyay, sir. Okay.
Yes, definitely.
That would be a good interaction, and many more things are there to learn from Dr. Subho Upadhyay. So, thank you so much, sir, for finding time out of your busy schedule. Now, I would request Mr. Shiv
Thank you,
Sankar.
sir.
Are you there?
Thank you, sir.
Yes, sir.
Please.
It is
Go
a
ahead.
pleasure to talk to you all, sir.
Thank you, sir. Thank you. Shiv Shankar, please.
Yes. Thank you, sir, for enriching us with your valuable words and esteemed presence. Also, I would like to thank all participants. Now, with this session is over. After a short break, Expert Talk 10 will start at sharp 3:45 p.m. IST.
Okay, as I have already communicated to all the participants that there is a small change in the expert top 10. Instead of Dr. Arvind R. Singh from Shandong University, China, due to unavoidable circumstances, he is not able to deliver the talk. Dr. Jitendra Kumar from Electrical Engineering Department, as you can already see him, he is on the screen. Okay, he'll be the resource person for expert top 10. Okay, sir.
Thank you.
Thank you so much, sir. It was really nice presentation. Thank you. Jiten sir, please.
Subho sir, thank you, sir.
Thank you, sir.
So
Thank
after a
you.
long time, I met you
Yes, sir. It is
online, sir. If I'll come to Agra, then I'll meet you.
I will definitely come, sir.
Yes,
Okay, sir.
it's really a wonderful place to visit, sir.
Yes.
Thank you so much, sir.
Jamshedpur also is a very beautiful place.
Yes, sir.
Please,
Please, do
come
sir.
here.
Please do come.
Yes,
We'll be happy.
yes, sir.
Okay.
Thank you, sir. Thank you very much.
Thank you.
So at sharp 3:45, expert talk time will start. Okay. Thank you. I'm just sharing the feedback form as well to the chat box. Thank you.
Okay. Thank you.
Hello, Shekhar. CS Shekhar.
Yes, sir. Yes, sir.
I think the time it's time 3:45. Yes, you can start now. And Dr. Jitendra has already joined, so
Okay,
please
sir.
introduce.
Thank you, sir. Good afternoon to all. Welcome to the online short-term course on recent trends in microgrid, that is RTM 2020. We now have Expert Talk 10 to be delivered by Dr. Jitendra Kumar, sir, who is currently working as Assistant Professor at the Department of Electrical Engineering, National Institute of Technology, Jamshedpur, India. Dr. Jitendra Kumar, sir, has received his BTech from IMS Engineering College, Ghaziabad in 2009, MTech from the National Institute of Technology, Kurukshetra in 2011, and PhD degree in Electrical Engineering from IIT Roorkee in 2007. Sir has over 4 years of teaching experience and taught subjects like power system, advanced power system, control and instrumentation, power system operation and control, signals and systems, power system protection, circuit and network theory. He has many papers in reputed journals. His major areas of research interest include power system protection and restructuring, protection algorithms design in smart grid and microgrid environment, design of protection algorithms in FACTS environment. Now, I would like sir to take session and enlighten us. Dr. Jitendra Kumar, sir, please.
Thank you, Shekhar. Thank you. So, Arvind, I think I got news that Arvind sir is not well. So I'm taking this session. Okay. I don't know whether I'm telling you something about the microgrid. Okay. So it is something, not the complete thing, because many more experts they have delivered the expert talks on microgrid. So I just want to share my PPT. So is it visible or not?
Yes, sir. Please go ahead, sir.
Okay. First of all, I just want to tell you that I'm doing currently I'm doing work in protection algorithms or islanding design algorithms in microgrid. So many experts have told you about the advanced things about the microgrid or smart grid, about the protection algorithms. Okay, so first of all, we have the definition of the grid. So we know about the definition of grid. So it is. So still, I'm reading it. An electric grid is a network of synchronized power providers and consumers that are connected by transmission and distribution lines and operated by one or more control centers. So it is a definition. It is okay, but we have interconnected networks. So many more networks are combinedly working, or I can say it is a synchronized way. It is working. Okay. So when we are talking about the smart grid, so there's one thing coming in our mind, that first of all, it should be the distribution system, and along with some local generations. So there are a lot of advantages of the local generation. We know about that can be a solar power, PV systems, or some wind systems. Okay, all those are the local generations. Okay, so here if we are talking about the power flow, so initially if we are not talking about the microgrid, so if the normal system, so we have some kind of generating stations, so that is nothing but a layout of power system. So initially we have the generating stations. After that we are sending some powers, okay, by a step up voltages through the transmission lines. Okay, so transmission lines are connected with the distribution centers. Okay, like substations or many feeders are connected to the distribution center or the substations. Okay, but when we are talking about the microgrid, so we have some definitions here. So a microgrid is designed, built, and controlled by customers based on internal requirements, subject to the technical, economic, and regulatory opportunities and constraints. So constraints faced. So here there are many aspects of the microgrid. First, there is a frequency mismatch. Okay, so first of all, whenever any system is connected to the grid, okay, so there's some issue about the frequency. Okay, so when we are generating some local generation, suppose we have the solar generation. So if we are connecting to the grid, okay, so we have to take first the permission. Okay, permission of the state electricity board or some kind of, then only we can connect there. Okay, so they can connect. Okay, so here if I'm talking about the microgrid, so microgrid having several aspects regarding power controller, voltage controller, frequency controller, or maintaining the PCC voltages. Okay, so it's nothing but a point of common coupling. So here I'm taking so again, so but yeah, if we are talking about the normal distribution system, so you can see we have the distribution substation, then we have the circuit breaker. We may have the connected loads there, or all those are connected through the n number of feeders. So it is a unidirectional power flow. Okay, so if it is a unidirectional power flow, so what is the difference between the normal distribution system and the microgrid? So in a microgrid, we have the smart inverters, some local generation, or we can say distributed generators. So we have the energy providers there. Okay, so if we have like that system, okay, if we are generating at our home, okay, so that is called the microgrid. Okay, so a complete grid, that is some kind of interconnected system, or here we are considering only one part of that one, only the distribution substation connected to the grid part. Okay, so you have to remember that one. Okay, so if we are talking about the controllers, suppose we have the local generation, then we are saying it is a microgrid. So in what is the difference between in a normal grid condition, if we disconnect the breaker, then that will be your passive, because we don't have energy at the rest of the feeders. Okay, but here if we are talking about the microgrid, so if we are disconnecting opening the circuit breaker, then we have energy to the feeders. Now that is a different thing. How can that energy will be distributed among the loads? But of course, that is not a absolutely passive thing. Okay, feeder network. So so that is the microgrid. If we are talking about the smart grid, so we are saying it may be we are connecting the several microgrids. Okay, but we have the control scheme will be okay. So so we should have some microgrid central controller. Okay, or we can say if so what is the meaning of this one? So we are taking the data from each connecting points. Okay, so so that we can control the inverter points. Okay, we can design the protection algorithm, we can control the power stability, we can check that one, or the angle stability. So if we are seeing all this kind of thing with the smart meters, okay, so that is called the smart grid. So I think smart means that if we have the facility of the advanced relay system, advanced control system, or sub communication networks. Okay, so that of course that should be in a synchronized way. If the system is not synchronized, then it may be a big disaster for us. Okay, so it is controlled by some control centers. Okay, so that control centers are called microgrid central controller. So I think we know about that one, but as per my knowledge, what I'm thinking, that we have some problem if we have the microgrid, or we can say local generation. So we may face a problem of the directional relay. Okay, so directional relay. What is the directional relay? So of course, if we are, you can see in that way. Okay, if in a first picture, you can see the power is flowing and it is dividing into the two networks. Okay, in second one, you can see there is some kind of fault. Okay, in between. So you can say the power is provided by the local generators. Okay, so in the red, in the second picture, the red mark is in a red mark, the direction of the power flow remains same. Okay, but in a pink arrows, you can see the direction will maybe different. Okay, so for the particular protection scheme, we need a strong directional element. Okay, so that can show the flow of power or flow of current, or we can say our scheme in such that it should take care about the direction of the fault. Okay, or suppose if we are talking about the fault, suppose if we have the islanding. Okay, in an islanding mode, what happens? So what is the islanding? So if we are just disconnecting the circuit breaker, okay, to the feeder system, so it is not a grid connected system, but local generators are providing the power to the rest of the feeder system. Okay, so in that way, our protection algorithm should work in such a way so that it can take care of the direction of the fault if any fault is there. So of course the power flow is changing. So in normal condition, in normal distribution centers, we don't have that problem because power is flowing in one direction. But here power can be flowing in any direction at particular point. So I think it is a so directional relay, we cannot ignore the directional element in the distribution system when we have the local generation. Okay, so now we may have some issues that I have taken from the transmission networks, but still we are facing that kind of issues in distribution system also. But I don't know whether we are facing or not. But of course, the directional having two problems. Okay, if so, what is the meaning of direction? So direction, the relay should be in that way that it can detect the particular direction. Okay, particular direction. Suppose a relay is made to detect for fault in a forward direction. Okay, so it will act only for the forward direction fault, not the reverse direction fault. Okay, if the fault on the back side, then relay should not operate. Okay, so that kind of property is called the selectivity property of the relay. So it can discriminate the direction of the fault. Okay, so now so of course we are facing that problem, voltage inversion. Of course, in a transmission line we are facing this one. So voltage inversion or current inversion cases comes into picture when we are applying some series compensation in a system. Okay, so series compensation may be fixed type, or we may have fact devices for that one. Suppose we have TCSC, it is a series compensator. So controlled compensation or uncontrolled. So uncontrolled means we are providing some capacitor bank. Okay, the conditions that voltage inversion occurs. So here we have some kind of system. We have you can see the figure, we have the VS. Okay, so XS is nothing but a source reactance. XC is a series reactance of capacitor bank. XL is a fault reactance. Okay, so in normal way, this is the inductive circuit. So in normal condition, your current will be 90-degree lag behind by the VR voltage. Okay, so how can we calculate the IR? So at the relay location, Vs divided by J, XS plus XL minus K, because we have the negative reactance for the capacitor. So at the relay point, if we have the VR, so how can we write it? This will be Vs divided by X, capital X, XL minus XC, or what is the value of capital X, XS plus XL minus XC. So now in that way, so in what condition your VR will be negative? 1 minute. So in what condition your VR will be negative? So of course we have if our XL minus XC, XC is greater than the fault path reactance. Okay, fault path reactance. So your VR will be negative. So of course it is a negative. So it will show in a opposite direction near to 180 degree. Okay. So if it is showing near to 180 degree, then it is a voltage inversion case. Okay. Or if we have, or in particular condition, if we have the XL plus XS is greater than XC, if it is so, in both cases simultaneously should be satisfied. Okay, for the voltage inversion conditions. So now, in what condition we have the current inversion case? So you can see the IR. IR is nothing but Vs divided by J XS plus XL minus XA. Okay. So if we have, so IR, in what condition IR will be negative? So I think your XC should be greater than XS plus XL. If this condition satisfies, then your IR will be negative and it is behaving as a, so it is behaving as a current inversion case. Okay, so XC is greater than XL plus XS. So your capacitive fault loop should be greater than XL plus XC. Sorry, XL plus XS. So in that case, also we are facing the current inversion condition. So of course, why I'm discussing this thing, because we are applying the capacitor bank on the distribution system also. So we may face that kind of issue in a distribution system, but generally we are facing that kind of issue in transmission lines system generally, because I have not seen that kind of cases in a distribution system, but still it may happens. So here we have the two types of microgrids, decentralized and centralized. So we have the certain advantages of the decentralized, means we don't have any common communication center, or centralized means we have at least one control center. Okay, so we have, of course, we have the advantage of the centralized microgrids, because we can control the functions of the other control schemes like voltage control, frequency control, or power control. Any kind of thing we can control in a one point. Okay, but in decentralized we have that kind of issues. Okay, so of course, if we have the communication system we are connecting some kind of communication system to decentralize, it become the centralized microgrids. So here we have some advantage of the centralized. So first one is the layer control architecture, device microgrid, defined functions, device local control and protection. So of course we know about that one. So I have already told you this one. So information exchange with the device and grid situation awareness, operation mode, power dispatch commands. So we can monitor each kind of things. Okay, limited dependence on microgrid control and communication, optimal power flow and energy utilization. So here we have some one important point here. So first one is the optimal power flow. Okay, so suppose we have to take care, there may be, if there is any overloading, so we may change in frequency, so of course we have to shut down some loads. Okay, so that kind of issues we are taking care with the centralized microgrid. So it is quite easy in centralized microgrid, but there's some problems. If we have the all point data, so maybe the protection system can be delayed to collect all kind of system, because we have some kind of communication delay. If we are neglecting the communication delay, then we are saying it is a good thing, but in centralized microgrid, if we are taking the communication system, so we may face that kind of issues. So in decentralized microgrid, we can design any system, any protection algorithm that can be immediately work. Okay, but it has a lot of disadvantages. So we have some kind of elements of the distribution system. First of all, what should be there? Okay, so measurement and control. So that we are discussing. So we have to measure, record, and control with the intent of protecting and optimizing grid operations. So all the protection algorithms or optimizing grid operations should be monitored. Okay, so that is an important thing. Substation part, if we have the control and monitoring system within a substation, we should have that kind of thing. Okay, so if we have the distributed generation, so we have the local generations, so we have extra source of power generation. So so we should have some kind of storage also. So suppose if we do not have, we should control a charging and discharging of an energy storage unit. So we should have some kind of storage of like battery. Okay, so I want to okay, fine. So we have the power protection system regarding microgrid. So it have ultimate emergency control. So it should have ultimate emergency control means, suppose if we have some firing in a distribution system, some kind of fault will be there. So that kind of abnormal condition should be stabilized. Okay, stabilized, or we have to remove the load part or anything. It is a similar power system. Okay, so that kind of thing we are also having in the transmission networks also. So in a distribution system, have some difference between that transmission system, but the issues remain same, because if we are connecting the load, so we are connecting the distribution system. Okay, so in more precisely, in a distribution system, we have to disconnect the feeders for a particular load. Okay, so in that way we can think. In a modern digital relays maximize the conflicting requirements while adding flexibility, adaptability, communications, and system integrations. Okay, so we should have the digital relays to operate, but we have some kind of attributes of the digital relay. So I want to tell you one thing. Then I have read that is a self-checking of the digital relay. So self-checking means what? So of course, the relay is used to protect the distribution lines or the transmission lines. But self-checking means if any part is if any part of that relay is not working properly, then the relay can take care itself, and it will adjust the features of the systems in such a way that that part will not work. Okay, so it doesn't care that part of the relay, or it can check the its health. Okay, actually I want to say. So protection system components. So here we are talking about so we have sensing devices like instrument transformers, CTPT, and sub sensing devices that can check the pressure, voltage, control, frequency of monitoring. That will help to monitoring the system health. Okay, so decision making devices like relay. So if it is detect the abnormal condition or the fault condition, so it should initiate the protection actions. Okay, so switching device, we have the switching devices like circuit breaker and the other switch gears, power supply devices, batteries, chargers, pumps. Okay, control circuits, we have cables and other auxiliary connections and control equipment, communication channels and devices. So for communication assisted protection, we have that one. Okay, remote indication, information storage. So, but what is the requirement of adaptive relaying? Okay, so here we are talking about the adaptive relaying. Okay, so first of all, generally in distribution system, we are using the overcurrent protection. So we may have many blinding protections. So blinding means I have already told you the importance of the direction relaying. So in normal feeder, we are generally using the overcurrent relay, but we need, of course, if we have the local generation, so we have the a directional element with that one, so that relay can operate in a correct direction. Okay, so in that way, if we are thinking that we have the blinding protections, means what, it doesn't have the features of the directional relay, then we may have some malfunction of the relay. So here I'm saying the directional feature is very important. Okay, so it may possible if system is working in an island mode or a grid connected mode, so it behaves different in a different way for the different types of fault. So in that way also, so the protection system should be adaptive in should work in both the conditions, like grid connected conditions or the islanding conditions. So here we had, so what is the adaptive relaying? So adaptive protection refers to the ability of protection system to automatically alter its operating parameters in response to changing network condition to maintain optimal performance. So what does that mean? So it is adaptive in nature. So it just check the conditions, okay, system conditions, and adapts that conditions and alter its characteristic accordingly. Okay, so but we here optimal performance is an important feature of this adaptive relay. So what is the meaning of that optimal feature? First of all, less time taking. Okay, so or best relay settings by which relay can operate fast. So it should have the best relay setting. Suppose it is it will take some time. Okay, so either we are saying that is the adaptive protection, or it will take time. So what is the need for that protection? Okay, so it should be fast. We have the sensitivity, reliability, selectivity, all those features of the normal relay. But if we are saying the normal relay, so in a adaptive relay also, that all features should be improved. So we have some adaptive protection in microgrid. This kind of system we can also use in transmission network. Okay, so in a transmission network, in any type of relay, we have that kind of feature. We are just dividing all the features of the relay. So we should have fault detection, fault classification, fault direction estimation, and the fault localization. I don't know, fault localization is an issue in distribution system, but still we have that feature. That feature should have. So we are dividing. So here, so of course, we have some MATLAB program. So some people having the different sources of that one. So but here how to use the fault detection algorithms. Okay, so in that way we are saying if we are connecting some AG type of fault, so you can see the current having current AG type means the phase A current will increase at the from the fault point. You can check that one, and volt is going down. Okay, so we have several fault detection techniques. Some basic techniques I'm telling you, it that can also be used in transmission line, but you can check that one also. So first one is the fault detection for sample to sample comparison technique. So here I'm not going into the advanced form of the microgrid, but I'm going for the basic thing about the microgrid. Okay, so we should understand how we have to design the algorithm. So first we have to understand the basic algorithm concepts so that we can design the any kind of algorithm, fault detection algorithm or fault direction algorithm, or any kind of algorithm we can design. So first of all, the fault detection algorithm. So here we are taking the difference between the two consecutive samples. Okay, so first of all, we should understand the sampling. What is the sampling? Okay, So here we are taking, first of all, we have to do the sample form data. Okay. So after that, only we can calculate the difference between the two samples. Okay, two consecutive samples. So if we are plotting that one, that I'll show you. Here in cycle to cycle comparison, here we are taking the difference of the one cycle. Okay. So you can change how sample to sample work. If we are taking the difference between the two samples, that is very less. But during fault point, it will be high. It will be more. So this will work. So in a cycle to cycle comparison, if we are taking the difference between the two samples after a cycle, so of course in a fault time, that will be the difference is large, quite large. So you can check that one if we have the fault current. Okay, in first part. So if we are implementing the sample to sample algorithm, so in pre-fault condition, it having very less value, but in a fault condition, it is quite high. Cycle to cycle, it in pre-fault condition, it having very less value as compared to sample. It has high value in the fault period, so that we can detect the fault. Okay, so we have some techniques of the fault detection. So phasor estimation. So some people are saying that is only a phasor calculation techniques. No, it is not. You can calculate any parameter from those techniques, or you can design the fault algorithm. Okay, so DFT is okay. So DFT is generally used to calculate what? Magnitude. So we know about the Fourier series. So here we have an, bn, the under square of an square plus bn square. So that is nothing but a magnitude of the fundamental frequency or its harmonic. So here we are calculating only the a1 and b1 for the fundamental frequency component for any type of. So we have some kind of DFT, 24-point DFT here we are calculating. Again, we have some technique, man-Morrison technique or Upadhyay method. So it is okay. I don't know whether you are understanding, maybe, but I'm not saying all these are good technique. Okay, so I'm telling you about the directly from DFT. So it is based on nothing but based on differentiation. So differentiation in a discrete domain, nothing but a difference. Okay, so here you can take the difference of the measured signals, then you can easily calculate a square, v square, or here we are talking about the v magnitude of that one. But I don't know these technique are using in nowadays. We are using generally DFT. So I am interested in DFT. So here we have the DFT formula of DFT. So VH equal to 2 by n summation n equal to 0 to capital N minus 1 Pn e to the power j and 2 pi h divided by capital N. Capital N means what? That is the number of samples per cycle or in a data window. Okay, so generally we are taking one cycle for a data window. Okay, so here Vn is nothing but a measured signal, or Vh is nothing but a magnitude. Okay, we are taking h equal to 1 for the fundamental frequency component, or small n is runs from 0 to 20. 20 means if we are taking the 1 kilohertz frequency, up to one cycle it should run. We have the if we are dividing just it into the cos and cosine and sine form, then only e to the power is divided for the cosine and sine form. So here we are calculating v magnitude is nothing but v real square plus v imaginary square to the power 1 by 2. So angle you can calculate easily. Half cycle DFT, here we are using only the half cycle. Okay, just n is replaced by n by 2. Okay, so your sample will go from n equal to 0 to capital N by 2 minus 1. So it will be the half cycle DFT. It is quite fast, but it left the negative half cycle. So it is a problem. Okay, cosine transform we have, but in the previous formulas we can calculate only the one cycle DFT. But what happens if we want to calculate the different DFT of the 10 cycles, 100 cycles, 1000 cycles, 2000 cycles? Then we have to calculate Thus, we have to use the sliding window technique. So in a sliding window technique, we are calculating a W1. So in W1, we are taking suppose we have the 1 kilohertz sampling frequency for 50 hertz. So here we have the 20 sample per cycle. Okay. So here for calculating the 20 sample per cycle, so new window will start if we are leaving one sample and we are adding one sample. Okay. So again, it remains 20. So like that kind of slide we are calculating for DFT. Okay. So if we are doing if we suppose we have the sinusoidal waveform on the upper side. So if we sliding window technique, we are calculating the magnitude and the angle. Okay. So again, we have the recursive DFT. So the calculation, suppose we have the ones that 20 sample per cycle. So we have the calculation of the 20 points. Okay. But here, if we know about the left sample or advanced sample, then we can calculate in a fast way. So here it is the formula. So VR plus 1 is nothing but a new DFT. VR is the old DFT, or e to the power j 2 pi by capital N plus 2 by N. VR plus capital N. This VR plus capital N is nothing but advanced sample, or VR is nothing but a previous sample, left sample. Okay. Whatever we have, leave that sample. So that is a value of VR, e to the power j 2 pi divided by capital N. So what is the advantage of this one? So here we have the single calculation. Okay. Not the 20 calculation. 20 sum will be there. Least square technique, that is very important. Now, so generally it is used for calculation of the magnitude and the angle, but we can also calculate the frequency. We can also calculate the power, or different types of parameters we can calculate using this method. Okay. So you should know the relationship between the measured quantity or the that quantity you have to calculate. So that is quite good technique and very powerful technique. Okay. So 1 minute. So here Vt is equal to V0 e to the power minus t by tau. So it is nothing but a decaying DC component. So tau is nothing but a time constant of the decaying DC component. So V0 is the magnitude of it. So if you are calculating the magnitude, it is quite important here. So summation n equal to 1 to capital N, Vn sine n omega 0 t plus theta n. So this is the mathematical part of it. So here we have to calculate we have some knowns, we have some unknowns. Here n is nothing but a harmonics. Okay, when n equal to 1, so it will give you the fundamental frequency component. If n equal to 2, it will give the second harmonic. N equal to 3, it will give the third harmonic. So it is nothing but a Vn is nothing but a nth peak value of the nth harmonic component, or theta is nothing but a phase angle of the nth harmonic component. Or if you are putting n equal to 1, it will be the fundamental frequency component. So how to calculate? So see the mathematical term, just open it, the binomial expansion of e to the power something. So higher order term we are just removing, V0 minus V0 by tau t, or this will be by some summation n equal to 1 to capital N. Here you can open just that formula for up to 5. Okay. Suppose we want to calculate up to 5. So V1 sine omega 0 T1 plus theta 1, V2 sine 2 omega 2 T1 plus theta 2, in a similar way up to V5. So each element component we have calculated. So now we have opened the first one, V1 cos theta 1 sine omega T1, V1 sine theta 1 sine omega 0 T1. In a similar way for the second harmonics, third line for the third harmonics, fourth line will be the fourth harmonics, and up to the fifth harmonics. Okay, the first two term is for decaying DC component. So now you have to separate what you have to calculate, or what are the knowns. Okay, so here you have to remember, in first term is V0. So V0, the known term is 1, or unknown term is V0. In second one, unknown term is V0 by tau or T1 is the known terms. But you know about the T1? Yes, of course. We know about the T1. So I'm telling you later. So in first term, we can see V1 cos theta 1 are the unknown, magnitude and phase angle, or cos omega 0 T1 is known, plus V1 sin theta 1 is unknown, or cos omega 0 T1 is known. So omega 0 we know about, that will be your 2 pi f. You know the value f, but how could we calculate the T1? So that is an issue. So here we are dividing some known and unknowns by putting T1 equal to m delta T. So m is nothing but a numbers 1, 2, 3, 4, 5, 6, 7, 8, or delta T is nothing but a sampling time. So suppose we have the 1 kilohertz sampling frequency, so your sampling time will be 0.001, yani 1 millisecond. So you should put that values and make all knowns and unknowns. You should understand. Now here, how to calculate the x? X is nothing but a pseudo inverse multiplied by V. V is what? V is nothing but the measured value at PCC. Okay, so now if you are plotting that one, to similar way you can calculate your magnitude is coming in that way or angle is coming in that way. Okay, we have done that kind of programming. So now here we have the frequency estimation technique. So we have that, suppose it depends on the zero crossing, consecutive zero crossing. However, it is not a very effective technique, because if we have some noise or some harmonics, so it can be crossed twice or thrice. So after using this technique, we need several filters. Okay, only this can be used, but it is not a very effective technique, but still we are using that one. So how can we calculate them? The frequency f Tm equal to m minus 1 divided by 2, 1 by Tm minus T1. So what is the m? M is nothing but a number of zero crossing. Okay, so Tm, how to calculate Tm? Tm is the ms zero crossing, or T1 is the first zero crossing. Okay, so if you are using in that way, calculate the frequency. Phasor, we have some kind of phasor based techniques also. So suppose if we are calculating f equal to 1 divided by 2 pi d phi by dt. So in a d phi means difference between the two phasors, okay, phase angles, or delta t, at what point you have taken it. Okay, so by taking the consecutive estimates, you can get the frequency of each point. But how frequency tracking? So frequency tracking is one of the part of the connection of the system. So if suppose we have the set frequency, so at the particular band, if it should be particular band, if it is violate the band, then your corresponding algorithm or any algorithm will take care regarding that one. But here I'm not talking about that algorithm, but the frequency loop should be like that. Calculate phasor assuming frequency. Okay, it may be 50 hertz, 60 hertz is written. I have taken from some another source. So calculate the frequency from the phasors. Okay, so is the frequency within the specified band around 5 hertz? Means it should within the frequency band. Okay, if it is violate the bands, then you have to set the frequency new f plus something, whatever the change you are getting. So you have to apply some different algorithm, then again set that value. Or if it is yes, it is in a band, then frequency is f hertz. So we have now we have some subsystem of the digital relay. So we know about that one, the signal conditioning, A to D converter, sample hold, clock processor. We have the advanced relay. So RAM, PROM is there, some storing devices, mass memory. We have the input, digital output devices, signal conditioner. Even we have the adaptive filters also. Okay, in that way. So the main thing is the search filters as signal conditioner. Okay. So so we have communication systems also in the digital relay. So this is the advanced relay. Okay, that kind of feature we have in advanced relay. This will be the inside view of the digital relay. Of course, it has the memory. That is an important feature of it. Okay, we can store more and more data on it. Okay. So I'm taking this last algorithm to you. Time domain algorithm for the calculation of system parameters. So that kind of system parameter you can also calculate with this algorithm. So here we are taking some VT and IT at PCC. Okay. So some L and R is the parameters. Okay, that you want to calculate. So VT is having VT equal to RT plus L di by dt. Here I forgot to put IT, RT, IT. Okay. So plus L di by dt. So if we are talking about the integration, so here we are taking the integration of that one. So integration of Vt dt, Ri dt, L di1 minus it0. So here we are taking the consecutive time. Okay, consecutive samples. Time corresponding to consecutive samples. In the next equation, again we are taking the next elements corresponding to a consecutive instant. Suppose we have the t0, t1, and t2 are the instant that we have that one. We are measuring the value on that instant. Here we are taking the values. Okay, so what are the unknowns here? R and L are the unknowns. Okay, so you have to calculate. So in a integration with the trapezoidal rule, you can be seen this rule in any mathematics books. Okay, so tk to integration of tk to tk plus 1 vt dt equal to delta t capital divided by 2 vk plus vk plus 1. So in that way you can calculate all the things. Here we are putting in a matrix form, so we can easily calculate. Suppose it is a 2 by 2 matrix. Okay, so here we are calculating R and L, but we have some problems here. Okay, we cannot so it is only the 2 by 2 matrix problem, but we have some issue with that one, because we are taking the complete samples of the one cycle. Okay, so your that both the matrix should not be a square matrix. So you have to take the pseudo inverse of first matrix and multiply with the next matrix. Okay, take the 20 samples, then only it will work. You will get the correct value of R and L. We have already checked that one. So we are getting the value of R and L with that one. Or of course, that may be one of the locator of the island, may be used in islanding or anything, or fault detection that may help you. Okay, so it is looking like a DFT technique. So you can use that one. Even DFT, not the DFT, but the least square technique. So least square technique is very useful and powerful tool to calculate the phasors. Of course, the phasors. But if you want to calculate the different parameters, you can also utilize the least square technique with the measured values. So that can be helped into the islanding detection. PMU technology. So it is okay. Micro PMU we are using, but I'm not telling you this one. So we have some fault direction estimation technique. Here we have calculated the superimposed current of that fault F1 and F2. Okay, so here we are calculated the angle using least square technique. So what is that? So it is the pre-value and the that superimposed value and the pre-value. Okay, so phi for the F1 and F2 fault. So we have to calculate the direction of that one. Okay, so there's one system that is connected, distributed energy resource connected to the grid. Okay, so relay connected to the G1 should provide the correct fault direction data. Okay, so in that way it will provide the correct result. So it is not my paper, but I have seen that paper. You can see this paper in IEEE conference maybe. So islanding detection techniques. So it is also not my proposed technique. So in an emergency case, I have to deliver this lecture. So that is why I have not put my techniques in PPT, but we have the several kind of technology. So if we are saying I'm just reading that how to calculate that index for the detection of islanding or not. So acquiring the voltage and current data signals, storing pre and post event voltage and current at sampling frequency of the 1 kilohertz, phasor estimation using the VWLES. It is nothing but a weighted least square technique. So estimation of the pre and post event negative sequence voltage and current, then compute the impedance, negative sequence impedances. Then you can calculate the index, or if it is greater than some threshold, then it will be your islanding, otherwise a non-islanding event. But I just want to tell you, you can take any kind of index. Okay, so it is a impedance based index. You can check any kind of. So there are a lot of works have already done in islanding detection area. We have the different techniques like passive techniques, active techniques, hybrid techniques, communication based techniques. So you can design using least square technique or DFT techniques. You can use that kind of techniques in that way. So if anyone wants to ask any question, please, you are welcome. Please ask the question.
Thank you, Jitendra sir, for such an informative presentation. Thank you so much. Actually, everybody knows that the schedule expert talk was from Dr. Arvind Singh from Shandong University, but due to some medical emergencies, he was not able to present his expert talk. So the session is now open for questions. We would welcome if there is any question or query. We would consider 2-3 questions. Yes, please. Or you can also write in the chat box. Sir, there is one question. There is one question in the YouTube chat box. Let me paste it here.
Okay.
Can we add inertia control algorithm? And that is from Shubham Tiwari, one of the participants, Mr. Shubham Tiwari.
Inertia control algorithm. Can we add inertia control algorithm? For what purpose, actually?
Yes, I also think that the question is, if you are listening, then please write your complete question so that
if you want to protect a small wind turbine power generating system, is it possible to accommodate to use such techniques? Yes, definitely. Somebody is saying Siddharth Joshi. So if we want to protect a small wind turbine power generating system, is it possible accommodate to use such techniques? Yes, definitely. You can accommodate any. It is if I'm saying the algorithm design, regarding algorithm design, you can develop any kind of algorithm. Okay, it is up to you, because it is some kind of man-made system. So you can use anything. We can add inertia control algorithm. I don't know what is that actually. In what way?
Actually, that is from the YouTube participant from YouTube. So with this, thank you so much, sir, for your presentation. That is really very informative. So
thank you, sir.
Student volunteer CSA, are you there?
Yes, sir. Yes, sir.
Please.
Okay, sir. Thank you, sir, for enriching us with your valuable words and esteemed prayers. Also, I would like to thank all the participants. Now, with this, the session is over. After a short break, Expert Talk 11 will start at sharp 5:30 p.m. IST. Thank you very much.
Okay, thank you, Omari sir. I- Without you, it is not possible. So
There
thank
is
you.
one more comment, sir, in the chat box. You can see yourself actually.
Okay,
I
sir.
think
It is a very, matlab, what should I say? It is a very good compliment for
I
me.
think Professor Sood has joined already, so he's saying thank you for a wonderful presentation.
Yeah,
Thank you, sir. Have you joined this meeting, sir? Can we see you, sir? Sood, sir?
sir, I want to meet you. I
Yes,
want to see you.
yes,
Okay, he is there. Yeah.
yes. Sir, kindly unmute your mic, sir. Voice is not audible.
Yes, I'm online. So I joined maybe about 20 minutes ago, and your presentation was already started, but I caught the tail half of it. Wonderful presentation.
Thank you, sir.
Very
Okay,
illuminating.
thank you so much, sir. How are you, sir?
I'm fine. Wonderful. It is very early in the morning here. I'm speaking from Toronto, so but as you can see from COVID related problems, we are now able to join across the world. So
Yes.
that is the good side of COVID. It has allowed us to be able to communicate in this fashion, and now the borders are all disappearing, and we can communicate right across the world, which is a wonderful thing. It is sad that COVID has taken so much of a toll, but you have to be positive about the whole thing.
Yes, really, sir. So, sir, we will be waiting for another around half an hour or so, then we will start, sir. Is there any problem, sir? So, if we wait?
No, there's no problem. I just wanted to join in and
Okay.
get some,
Okay, sir.
So I will be online from now on anyway, so
Okay.
no problem.
Okay, sir. Okay, sir. We are really happy, and it's all our pleasure actually to have you.
No, it's thanks to you. You have done all the hard work to put this together. And if it was not for you, it would not have been possible to get a session like this one. I'm looking forward to more interactions with with all of you. So.
Yes. So thank you so much, sir. We are also online, and by the time we'll start the session, your expert talk. So thank you, participants, and next session will start sharp at 5:30 p.m. Indian Standard Time. So thank you so much. Hello. Mahanti sir, are you online?
So first unmute yourself. First unmute yourself. Manti sir.
Mahanti sir, are you online? I saw him. I think he's online, but maybe
He has connected. He has connected.
Okay. Okay, Shaili, are you ready?
Yes, sir.
Yes, sir. Okay. So, is it audible, Sood sir?
Yes, it is audible. Everything is fine. I can see the screen.
Okay. Okay, sir. Okay. So, I would request Shaili to first. It's still 1 minute is there, so please wait for 1 minute, Shaili, and then you can start introducing the speaker, right?
हो गया sir, हो गया.
Okay. Yes, you can.
Welcome to the online short-term course on recent trends in microgrid RTM 2020. We now have Sport Talk 11 to be delivered by Dr. V.K. Sood sir, Associate Professor in the Electrical Engineering Department, Ontario Tech University, formerly University of Ontario Institute of Technology, Oshawa, Ontario, Canada, where he joined in 2007. Sir is also a professional engineer in Ontario. Dr. V.K. Sood sir was a senior researcher with the Research Institute of Hydro-Quebec, Montreal, Quebec, Canada for many years. Sir has received the PhD degree from the University of Bradford, Yorkshire, England, UK in 1977. He has authored over 150 articles and written 2 books on HVDC and fax transmission systems and has been the editor of IEEE Transactions on Power Delivery, associate editor of IEEE Canadian Journal for Electrical and Computer Engineering, and associate editor of IEEE Canadian Review Quarterly magazine. His current research interests include the monitoring, control, and protection of power systems. Dr. V.K. Sood sir is a Life Fellow of the Institute of Electrical and Electronics Engineers, IEEE, a Fellow of the Engineering Institute of Canada, and a Fellow of the Canadian Academy of Engineers. If I speak further about Dr. V.K. Sood sir, this session would not be enough. Hence, I would request sir to take the session and enlighten us. Sir, please.
Thank you, Shali. First, I would like to ask if you can see my screen.
Yes, sir. Quite clear, sir.
Quite clear. Okay, you can hear everything. All right, so I would like to say thank you very much to Dr. Om Hari Gupta for inviting me. I would also like to say thank you to Jamshedpur NIT for the opportunity to be able to present today. So what I'm going to present is a project that we undertook in 2014. This was the Ontario Tech. Ontario Tech is the university where I work. Previously, it was called the University of Ontario Institute of Technology, but last year we changed the name to Ontario Tech University. So if I mix up Ontario Tech and UOIT, it's the same institute, just that the name has changed in the last year. So this is a microgrid project that is on campus. It is the largest microgrid in Canada on a campus so far. I don't know how long that will last, but at least for the time being, it is the largest one. So I'm going to share some of the experiences that we've had with this microgrid, and where are we going in the future with this one. So with that little introduction, let me give you some look at the actual project. I will go into these pictures in a little while in more detail, but this gives you an overview of the whole project. The project was started in 2014 with a grant from the Ontario government, $2.4 million grant to install a microgrid on the campus of the university. We subsequently managed to get various partners to come on board and donate some of their equipment, etc. So by the end of the project, this was like a it was an $8 million project. The initial grant money from the Ontario government was utilized, but then the various partners chipped in their in-kind contributions, plus equipment, plus other benefits that they provided. So this gives you an overview of the whole project. The partners, the principal partner was, get my laser working, all right. So the principal partner was Panasonic. They're a Japanese company, and they provided the battery pack for the storage, lithium-ion batteries. General Electric was one of the partners which provided the control system, the monitoring system. And the two utilities that were involved, the local distribution company was Oshawa Power and Utilities Corporation. And the transmission operator involved was Hydro One, which is the big transmission operator in the province of Ontario. So with these partners, UOIT Ontario Tech was the location. So here you can see the 44 kV grid. I will show you some detailed pictures later. And this was the in-feed. There were two lines coming in, 44 kV lines coming in. This was the motorized switch, which was utilized to connect and disconnect. This is a look at the 44 kV substation, which was part of the OPUC installation. You can see 4 diesel generators over here. This was the Panasonic cubicle with the lithium-ion batteries in there. Over here we have the CHP plant, which is the combined heat and power building. This was 2.4 megawatts. Behind here was the CERL building, which is the clean energy building. This was designated as the critical load. This is part of the campus, and this building is called the ACE building, the Automotive Center of Excellence, which belongs to General Motors. This was a particular load. This building with the power factor was very, very low. In here, in this building, there is a wind tunnel which has motors. And when those motors come online to operate the wind tunnel, the power factor takes a nosedive and it becomes quite low. And we used the microgrid to try and improve the power factor and to reduce the infeed from the grid. This was the monitoring and supervisory control system, the SCADA system from General Electric. Inside this cubicle, we have the converters, the AC-DC converters. This is a look inside the Panasonic converter with the lithium-ion battery packs. This is the look inside the CHP plant with the gas turbine engine in there. This is a look at the laboratory, the clean energy laboratory. On top of this laboratory are the photovoltaic cells. The panels are put here, 150 kilowatt generation capability. This was the switchyard with the CT and PT monitoring systems. The monitoring display, the battery monitoring display is shown over here. So this gives you an overview of the whole project. So what was the objective of installing this microgrid? So the first objective that the government of Ontario wanted was to develop and demonstrate an islanded but grid-tied smart microgrid and determine its ability to operate in isolation from the external grid. It was to provide enough electricity to power the first priority critical loads on the campus if there was a disruption from the main grid, such as during a storm, until overall power was restored. But one of the strategic reasons that this microgrid was formed was that because the university campus is a designated evacuation center inside the Durham region, next to Durham region, we have 2 nuclear plants within 50-kilometer range. So after the disaster in Japan, the nuclear power problem, the tsunami over there, the government felt that with the nuclear power plants in the vicinity, there was a evacuation center needed, and the university campus provides this evacuation center, and therefore a separate source of generation, a microgrid, was required for the campus, and that was the primary role that this microgrid was installed at this campus. A third objective was to offer a test facility for a smart microgrid development and provide some innovative research for the professors, the faculty, students, and associated industries around Durham region to improve the performance and reduce the cost of microgrid systems. Many utilities now are very much interested in adding on renewable energy, and the reasons for microgrids are now becoming much, much more obvious. So if you want clean energy to be incorporated into the grid, then the formation of a microgrid becomes quite crucial. So with these 3 objectives, the project was started in 2014. And last year in 2019, after a delay of 1 year, our planned operating date was in 2018, the end of 2018. but due to unforeseen problems, the whole project was delayed by 1 year. And in 2019, the microgrid became operational. So we have had yet less than a year of operating experience with this microgrid. So we are now beginning to learn quite a bit and see how we can improve on this technology. This was my team of students. I had various PhD students and master's students. I have now Haytham Galgawad has graduated. Ali Sambul has graduated. So these two students have graduated. I still have Ignesh Kumar Patel, Ahmed Shir, and Yusuf Al-Haj. Gagandeep Sharma will be graduating in a few months. And Priya Balasubramaniam is here. And then Yadunath Sapkota is still with me. So this was the research team that I had. And this gives you an overall look at what a microgrid is. It contains all the various components that form a microgrid, and you can probably relate to this. I mean, you've heard talks before on the microgrid this session, and you can relate to some of the components that I will talk about. So in a typical microgrid, here is a grid, a PCC, a point of common coupling, which may or may not be connected to the grid. So here is the grid connection. So this is normally a distribution level grid. So therefore there will be impedances, and we can consider a relatively weak grid if possible. There will be some kind of transformer that isolates the grid from the microgrid. And then we have something called a main switch, which is called a fast transfer switch, FTS. So this switch is crucial it has the responsibility to disconnect from the grid and then reconnect to the grid when required. And because you want this to be a fairly seamless kind of transition, disconnection and connection, you need a relatively fast transfer switch. Now, the terminology that people utilize, fast transfer switch, means very many different things to different people. And one of the things I wish to highlight over here is that although these components in the microgrid are all well known individually, when you bring them together, suddenly new requirements become apparent and new modes of operation become apparent, and you begin to realize this block or this component has a duty cycle which you never envisaged before. So normally we have a load on the microgrid which is fed from the grid when the grid is available, and when the grid is not available, then the microgrid with its renewable sources will supply the load. Now, in our case, in the microgrid that we had, the campus load was roughly 8 megawatts. The availability of the renewable sources and the generation that we had is only about 4 megawatts, about half. So therefore, when we lose the grid, we cannot supply the 100% load required by the campus. So we have to shed approximately 50% of the load so that we can keep the critical load, like the computer services, for instance, that is crucial, the lighting and the emergency services, etc. Those have to be kept on, but then all the other loads can be shed. So we had a photovoltaic system, 150 kilowatt generation photovoltaic not lithium ion, but polycrystalline cells. And of course, we need, because this source is a DC, fluctuating DC source, an AC to DC converter is required to connect these two to the grid. We also had energy storage system. This was a lithium-ion battery pack, 500 kilowatt hour. And of course, we needed a AC-DC converter to tie that to the grid. And then there was the CHP plant, which was a generator, gas-fired generator with its turbine. And that was also connected to the grid. And this was roughly 2.4 megawatts. Not shown over here are 4 diesel generators. And those diesel generators can be fired up when the situation demands. Remember that diesel now is quite expensive and it's a fossil fuel. So we don't want to use that. But should the requirement occur, remember this was supposed to be an evacuation center. So if we lose the grid for whatever reason, then we need to supply this load, then the diesel generators do kick in. Our peak load in Durham region occurs during the summer because of the air conditioning requirements. And this gas-fired generator, the CHP plant, is then brought on to serve as a peak load supply. It takes about 10 minutes to fire up. So we can very quickly get this up and running. The diesel generators take longer. So these are the various components that were involved. And these little stars shown over here are the various monitoring points, the sensors, which play a crucial role in the operation of this microgrid. Especially when you go into islanded mode, you have to detect islanding, and then you have to operate this switch. When you want to reconnect, then you want to monitor both sides of the switch to be able to make sure that you can reconnect without causing too much disturbance. So this fast transfer switch then plays a role. So over here, all these elements now begin to take on a life of their own. And they become quite crucial because now everything has to function together in relationship to the other components of the microgrid. As I mentioned, this load over here was a particularly bad load at times, especially when the ACE building came on. So the power factor goes down. So what we wanted to do was we wanted to make sure, because we were paying a heavy penalty to the utility because of the low power factor, we wanted to utilize these sources to see if we could supply this demand and keep the required amount of energy that we took from the grid. We were not planning to feed back power to the grid. We could, but we were not planning to feed that energy back into the grid. So although the capability exists to have bidirectional flow of power, we were not planning to do that. We were only planning to reduce our demand from the grid. So now you can see the various basic components of the microgrid. And of course, tying all these things together, you have to have some kind of management system, and energy management system is required. And this energy management system has to have communication requirements so that you can control the sensors and the switches, etc. So we needed two levels of energy management system or control systems. The SCADA system came in. So there was a local control system, and then there was a supervisory control system. So two levels of control systems were needed. And on top of that, we have to have the communications so that we can monitor these points and then send the signals back to the control center and then do the controlling from there. So a wireless communication system had to be built. The whole campus is roughly about 3 kilometers spread out. The various elements are about within 2 to 3 kilometers. So we needed a wireless system to be able to communicate. Putting in hardwired links for communications were very costly and expensive. So we decided to go on a wireless method. So this gives you a little bit more detail. So here is the energy management system. So this was a supervisory controller over here. And then, of course, we had a power input signal going in here, and that would be sent down to local level controllers. And then we could operate the power converters. So over here, we had the DC input from the PV or the battery, and that went through some kind of converter. And then, of course, we had to control this one. Sensors came into play here, and feedback signals were brought into the local controllers, and they were also sent back to the supervisory controller. So then the connection to the AC grid, also the local distribution company was required also. So this gives you an overall look at the overall system. So by now you have probably gathered, the question is, what is a microgrid? You've probably understood what the microgrid is now. Basically, it's a small-scale replica of the main power grid. It has each and every component that is in the main grid, the generation, the loads, the controls, the switches, etc. Everything is there. And we needed microgrids to bring distributed generation closer to the consumer. And remember that the consumer is now going to be called a prosumer. It is also going to be a producer. So there's a changing paradigm. Our utility is going to be a very different thing in the future. We are hoping to be much more flexible and much more efficient. We are also going to be cleaner, sustainable. Most of these microgrids are now operating at the distribution level, although they can operate at the transmission level, voltage level as well. But most of them are being applied at the distribution level. And you want to make sure that when you have this microgrid, you can still enjoy stable operation. We are used to having a stable operation from the grid following any kind of disturbance. So we need to maintain that kind of operation. The microgrid has to have two kinds of operating modes, either grid connected or in islanded mode. Now, in the grid connected mode, of course, the microgrid voltage and the frequency is maintained by the grid. The DGs act as constant power sources and inject demanded active or reactive power, what we call the PQ mode, into the grid. Alternatively, in the case of the islanded mode, the DGs supply the power to the local loads, and the DGs maintain the voltage and frequency, what we call the V by F mode of operation. And of course, we have to maintain the limits as required by the operator. So we can only change the voltage by a few percent, and we can only change the frequency by a few percent. So these are the two different modes, and the control modes, either PQ mode or the V by F mode, need to be understood. This gives you a look at the specification. I've already mentioned some of this. The campus existing 1.6 megawatt diesel generators plus the 2.4 megawatt combined CHP plant. This was added up there, so you can see we had roughly 3 and 4 megawatts generation capability from the diesel plus the CHP. On top of that, we had the PV, which was very, very small, 150. This is 150 kilowatts. And we had this battery, 500 kilowatt hour lithium ion battery as the storage system. So we were supposed to balance this 4 megawatts of load during a power outage. And we were supposed to facilitate a new working laboratory. So this is like a living laboratory for my students and the campus, so that we can learn about microgrids and what have you. This is the one-line diagram of the actual system. I won't spend too much time, but basically you already have an idea of this. These are the partners. Like I said, Panasonic was the lead partner. We had Ontario Tech and Oshawa PUC. That's a local grid company. Then Hydro One as a transmission company, and the General Electric as the SCADA and the monitoring system supplier. So here is the look of the actual equipment, and so here is the 44 kV in-feed coming in. We have 2 feeders. The second feeder is not live yet. Only one feeder is being utilized. This was a motorized switch, and it's funny that this motorized switch is supposed to be the point of connection. And when we first came to operate this switch, we had a whole team of people waiting to connect. And of course, this switch broke down at the very first moment that we tried to operate it. It had not been used for over 2 years. It was stuck. And when we tried to force it, it broke. And when it broke, of course, then we wanted to get spare parts. And we couldn't get spare parts for this immediately. It took us more than a week to get that. So these were the kinds of delays that occurred that were unforeseen. And that caused a delay of over 1 year in the project. This is a look at the power converters. These are supplied by Dynapower. So the rating is shown over here, 600 volts AC. They can range from 840 volts DC to 600 volts AC. So it gives you the nameplate. This is a look at the lithium-ion battery pack. This is the monitoring display inside. This is a look at the inside of that cubicle. This connection was underground. We had to make this connection to the building underground. So we had to dig that foundation over there. And you can see that this is the temperature of this cubicle is controlled. We are in Canada, so the temperatures can vary from plus 40 in the summer to minus 40 in the winter. So it's a big temperature change, so we have to control this. This is a look at the 2.4 megawatt gas-fired engine CHP plant. Now, like I said, this takes 10 minutes for us to start up. And this is enclosed in this building. This is the cell building, which was the critical load. It's not really the critical load, but we designated this as a critical load. The PV cells are on top of this building over here. So this building was designated as the critical load. The CT, PT metering system, this is in the switchyard in the substation. This is the famous ACE building. Very low power factor, like I said, because of the wind tunnel. The wind tunnel is in this portion here. So this is another look at the Searle building, the laboratory. This connection over here, this loop over here, is the connection to the PV cells, bringing it into the building to house the SCADA center, and everything is done inside this building. So this is a look inside. So here is the SCADA system. The monitoring system is there. And this was supplied by General Electric. This was the team, I said, that operated the microgrid. And this was the crucial day that we started. And on the 14th of August, we were waiting for midnight to get access to the facility. Of course, one of the things is when you retrofit a system into an existing system, the campus was already there, and we wanted to put this microgrid in operation. So everything has to be timed. So when the university is quiet, all the students and faculty and all the buildings are quiet at that time. That was the time when we had access to go and do our work. So we were sitting there waiting for midnight. And at midnight plus 10 minutes, when we tried to open that switch, that motorized switch, then of course it broke down. And you can see the whole team kind of sitting there twiddling their thumbs, trying to wonder how to progress. So it becomes quite an operational exercise to make sure everything functions. So it's quite a task. I've already talked about the various partners. This is the MIMIC panel of the microgrid, and you can see all the connections. So this is at the SCADA unit, and we can monitor now how much power is coming in, how much we are taking in, and so forth. So the CHP plant is over here. This is the battery pack over here. So we can monitor all the various points now. So like I said, we've now started monitoring, and we have less than 1 year of operation in service, and now we will take this further and analyze the results and see how successful or unsuccessful we have been in our original estimates and so forth. So, excuse me for a second. So here is a model, a simulation model, and we tried to model the various components. And this was built up in MATLAB. So we tried to model the system, and you can see that there is the battery pack, the photovoltaic, the critical load is indicated, the connection to the grid is there, the load is indicated over here. So the fast breaker switch is indicated, transformer is there. So now there were a couple of transformers over here, another transformer there and there. So these transformers now start taking and playing a role in the operation and behavior of the system. So especially when we have these fast switches and you connect and you disconnect the grid, things like inrush current and into the transformers now begin to make life interesting. So when we looked at this model, you look at the various elements within this. So here is the battery. Here's the photovoltaic, the critical loads. These are nonlinear loads. You have to monitor the control systems, etc. Now they begin to take a life of their own. And even like I said, the switches over here, they become quite crucial elements. So when you start looking at the model of the PV, so the PV is modeled like this. This is quite a common algorithm that is used for the current coming out from the PV, and these various factors. I won't go into the details of this, but this is a well-known model of the PV, and so you start modeling this in much greater detail. Here is the battery model. Even the battery becomes it's not just a simple source. It's really a controlled voltage source. And it has an internal resistance. And the charge on the battery has to be monitored as well. The state of charge of the battery plays a role, because one of the things that Panasonic, who supplied the batteries, wanted to look at, they wanted to see the charging and discharging cycles of the battery, because the life of the battery is dependent on that. How many numbers of cycles of charging, discharging you go through, what is the state of charge of the battery, and how quickly you charge the battery and how quickly you discharge the battery. So the model of the battery also had to be detailed enough. So it's a controlled voltage source. It has an impedance. You have to monitor the state of charge of the battery. So you monitor the current coming in, you integrate that to give the state of charge, and then you control that. So the charging voltage and discharging voltage can vary according to the algorithm. So that becomes quite a detailed model as well. The boost converter, it's a simple DC to DC converter. And when you look at a DC to DC converter, well, it's nothing new. People, even undergraduate students, learn their basics on that. But now when you put that in cascade with an AC to DC converter, and two converters have to operate together, now interactions start taking place. And you begin to see the differences and the interactions taking place. And you want to see and monitor the behavior of these converters. So there is a MPPT, a maximum power point tracking, because you want to make sure that the PV is capable of giving you the maximum power that you can utilize. So there's an algorithm that does that. And we use this is another well-known technique, the IC, the incremental conductance method, which is an MPPT technique, so that we can maximize the energy coming from the PV. The AC-DC converter is a voltage source inverter. And these equations, again, dictate the behavior of this. Now, you have two converters in cascade, and you want to make sure that there are no interactions taking place between them. The control strategies, now again, this voltage source converter has two control loops. One, of course, we mentioned the P and Q control loop. And then there's an inner control loop, which is based on the current. So we have different loops inside the converter. Then we have to switch the mode of operation, because now we are both operating in islanded mode as well as connected mode. So if you want to go into V by F control mode, then the controllers have to be switched over. So here are some of the results. So this is the bidirectional converter. So when we were in active power control mode over here, you can see that this was in the inverter mode and this is in the rectifier mode of operation. So a change in the power, and we can see that the measured power and the reference power, they were tracking each other very quickly, very nicely. In the case of the rectifier, we also saw that. These were tested over there, and you can see that the behavior of the controllers. We mentioned particularly islanding, and earlier on this morning, you had presentations from another speaker, and he mentioned the detection techniques when we go into islanded mode. So we can have various types of detection, passive, active, or hybrid. We used, for the time being now, remember this was supplied by a partner, General Electric. So they used a passive detection mode. This is according to IEEE 1547 standard. And in this standard, of course, we have under voltage and over frequency detection logics. So voltage and frequency detection modes are there. So you monitor in the case of the voltage, you monitor the PCC voltage, and then within ranges of 1.2 per unit, 1.1 per unit, 0.88 per unit, and 0.5. This is in the 1547 standard. And there are some delays incorporated in there. So we could use these passive detection mode to detect under voltage or over voltage. The same thing we could do with the frequency mode, frequency detection. So our system is 60 hertz. So 60.5, 59.3, and 57 hertz. So under frequency and over frequency detection modes were utilized. Using this kind of detection technique, we could decide on islanded mode of operation. So here is a case of an islanded mode of operation. So there was a fault applied at 1 second at this location. There was a fault on the system on the PCC. And you can see the voltage, which is the red signal. Of course, the voltage detect was down, and the delay, the under voltage logic took some delays according to the passive detection mode method, and we were able to detect that and go into islanded mode of operation. At the same time, the under frequency logic, the over frequency, you can see that the frequency went out because the voltage was down. So here again, the logic came into play after the delays, the built-in delays. And you can see that the various circuit breakers were operating with those delays. So you could see that we went into V by F mode at 1.3. Somewhere around here, we went into V by F mode of operation because we were now islanded. The breaker tripped at 1.32 seconds. There was a delay of 150 milliseconds. So this technique works, but it has its limitations, and various other detection techniques. Like I said, you can use the passive or you can use active methods. And one of the ideas of having a living laboratory, I mean, this microgrid is now functioning, but now the research team is going to develop new algorithms and new methods of controlling. If you can do a better job than what was existing out there in the marketplace. The whole idea of a living laboratory is to be able to take this to the next level. So now the research aspects are going to kick in, and we are now going to develop our own algorithms, active methods and hybrid methods, to be able to detect when we go into islanding and how we change the mode of operation, etc. So the research aspects are now going to come in. We have the laboratory in place now. We have a basic system, a standard system in there, but now the research aspects are going to be developed further. The machine model, we talked a little bit about the CHP plant, which is a generator. It's a machine model. So that has to be modeled in detail now. Right, so it's a synchronous machine output. So we started modeling this. The turbine model has to be developed. The information that we got from the manufacturers was quite limited. And sometimes when you have a practical system in operation, sometimes getting the data is not an easy task. And we find that some of the data is missing. And then you have to come up with your own estimates and see how you can best model the system that you have to replicate the behavior and then to improve it. So here is the excitation model of the machine. And again, this is much more detailed. So it has various compensators in there. The damping has to be there. This is the behavior of the machine dynamics now. Remember, when you go into a V/F mode of operation, the frequency and the voltage now is controlled by this machine, this single machine that is there. It's a small machine. So the dynamics of this, because this is now separate from the grid, it has its own dynamics. Now you have to look at that. So you start looking at those. I mentioned the requirement for the fast transfer switch. And when we purchased this fast transfer switch, the manufacturer told this is very fast. It is seamless. You won't see any differences, any changes. The system is so fast, it will switch off and it will switch on and disconnect from the grid, and it is seamless. And when we started probing into this word seamless, how seamless is it? Reality sunk in. And seamless, what the manufacturer tells you and what you think is seamless are very different things. Remember, you have to monitor both sides of the breaker to be able to operate this breaker. And you need to synchronize both the voltages on the line side and the load side. And you require some phase lock techniques to be able to do that synchronizing. So that has issues of its own. So here is a very simple example of, you have a main source, which is the grid, and you're connecting to the load. And there's the backup source, which is a microgrid. So you have two different sources now, which you can feed into the grid. And this switch is supposedly a fast switch. It's an electronic switch. But the manufacturer told us this is seamless. We will not, when you switch off and you switch on here, you wouldn't detect the behavior. But in reality, what happens, there is an incorrect transfer in the case of an upstream fault. If there's a fault over here, on this side, on the line side, then if the switch doesn't open, then the backup source comes on, you actually start feeding into this fault. And this kind of behavior can make life difficult. So we have to take the behavior of this fast transfer switch in a much more critical way and try to analyze this behavior. And we are now beginning to make some further research into this activity. Like I said, the control and the voltage detection is required. You need to look at both sides of the voltage and then synchronize. So you need to have a technique which allows you to synchronize. So this was some of the detection schemes that are incorporated with this kind of transfer switch. Finally, a few words on the energy management system. We saw this microgrid. This is the same picture that you saw earlier. But now from the energy management point of view, we used a PSO algorithm to be able to generate the power order. So we looked at the system constraints. There was an objective function that was created. System variables were monitored. So we had the wireless signals coming in. The objectives, cost function, emission objective functions, or multi-objective cost functions were required. System parameters were monitored. System constraints were applied so that we could generate a power order. So this energy management system at supervisory level is quite complex. So we can use different algorithms to optimize this. The communication side, mentioned that briefly. There are communication requirements over here, and of course to do the monitoring. And we use a wireless communication system, so we had to do some tests on that. So what are the kinds of signals that we were monitoring? We had digital signals and analog signals. The digital signals were the control parameters from the breakers, on or off. The analog signals, which were the monitoring signals, control signals. We had to match the load demand to the generated power by the DGs to enhance the reliability, efficiency, and the stability of the system. So the communication system introduces communication delays into the feedback path. How much is the communication delay and what is the impact? So that, again, so we had to develop a communication system, a wireless communication system. So my students were looking at some of the available techniques. So we use this wireless transceiver in our F24L01. And this gives you some of the ratings of this one. We used the Arduino controllers, the micro controllers. There were two of them, Arduino Uno, which is a very low-cost device. So one of the requirements was that we needed a fairly low-cost communication system that we could develop. So the Arduino Uno is a very low-cost chip processor. The bigger one is the Arduino Mega, which has the same capability, but it has more pins. So over here, we only have 6 pins. Over here, we could go up to 16 pins. So more signals capability. These are some of the results. So when we looked at, because one of the ideas was to find out what is the delay in the communication, what is the latency. So 2 tests were done, one for the digital and one for the analog signals. So with the digital signal, we sent in a 1 pulse signal, 1 hertz signal to open or close the breakers. And then here is the look at that. So this was the actual signal that was sent out, and this was the delay. So there was a delay of 1.6 milliseconds from the actual signal to the signal that was received at the control center. So this delay had to be incorporated into the algorithm to be able to make sure that the control system could keep that in mind. We did not have a number for this, and we needed to have an actual figure to put that in the loop. In terms of the analog signal, again, we put in a 1 hertz sinusoidal signal. So you can see that there's an input and output. This is the transmitted signal is in yellow, and the signal in green is the received signal. And we noticed that there was a 10-degree phase shift in the transmitted signal and the received signal. So again, this phase margin had to be incorporated into the system. And with that, I hope I've been able to give you an idea of a microgrid project. You take it from the ground, you bid for the project, and you see it till the end. Like I said, now we have a system working. It is functioning, and it has been functioning for the last year. We are now beginning to get results and so forth. So now the next task will start. How to improve on what we have. And that is a task that we are going to look forward to in the next few years. Well, thank you very much for listening. And if you have any questions, please feel free.
Thank you very much, Professor Vijay, sir. Can you hear me?
Yes, I can hear you, yes.
Thank you very much, Professor. This is Imad. I'm speaking to everybody here from Dubai. And I would like, first of all, to thank Dr. Professor Omhari, sir, and for the team for inviting us to join this beautiful presentation. Actually, for our surprise, this is the very first time that we know that there is a research fully-fledged, what they call it, microgrid inside a university campus, which is huge. And we thank you, Professor, for this insight, and we would like to thank all the sponsors for this huge project. Actually, I have 2 questions, Professor, if your time will allow me. The very first question is about the cyber physical security of the system. Actually, we did not see that you superimpose or you've presented in this presentation. Is it going to be a plan to consider the cyber physical security of the system in the future?
Very good question. Thank you very much. Yes. The short answer is yes, we are going to consider the cybersecurity aspects to this. It is a work in progress right now. We have not done any work on the cyber aspects, but it is a project in hand. So when I get a student, COVID over the last 7-8 months, as you can appreciate, has caused further delays. This is something that you have to live with, and so I have not been able to recruit new students over the last 7 months.
Understood, Professor. Understood. Thank you very much, Professor. Understood. Actually, we are doing some research with Georgia Institute of Technology nowadays. They have what they call cyber physical security master degree, and I'm one of their students. And we are looking to places where we can do our practicum, which is five credit hours. If chances will allow, we might visit you, Professor, in Ontario, Canada, inshallah. Me or any of
look forward to it.
Okay.
Professor, I have a question.
Yes.
I am Dr. Sharmila from Anna University. Can we design a microgrid exclusively for EV charging application? If so, have you done anything on that, Professor?
I'm sorry, Professor. Could you repeat your question, please? I lost communication.
Yes, Professor. Do you have any DC microgrid exclusively designed for charging the EV charging infrastructure? Because in India, it is very primitive now, EV penetration. But in the other developed countries, I have heard very large number of charging stations are available. So how far Canada has attempted in implementing a microgrid for EV charging? Is it a viable option? Two things I'm asking, Professor.
Yes, it is viable. We have work in that area with the DC microgrid in operation right now. I'm not involved with it directly, but there is one installation in Burlington, which is taking place. I have just published a paper with a DC microgrid it's a simulation study. If you leave me or you write to me via email, I will be able to share some information with you on that aspect.
Yes, Professor. Thank you very much, Professor.
Yes, it's my second question, Professor Omar, if you allow me.
Yes, please.
Okay, Professor, my second question was about the control system. You are looking for somebody or some student to model the system, the generators under different conditions. Is this what we understood from the presentation? Is that correct?
Yes, that is correct. As I mentioned to you, if I can just share my slides again with you.
Yes, sir. We are thanking you.
So this is the present state of the research project. The idea is to build a model of the microgrid, the actual microgrid. So now the next phase is to connect the CHP plant. The CHP plant is not included here. So the next objective for my student is to add the CHP model, which is based on this model, and this has to be incorporated in there, and that is the next phase of the work that we are undertaking.
Excellent. So because what's the reason of my question, that this can be done easily with the machine learning and neural network and fuzzy logic implementation and system modeling.
Yes, that is quite true, and we are looking at. See, one of the things is you must have heard about inertia, the lack of inertia in the microgrid, because now there's only a small machine over there. So there is hardly any inertia. You have converters that are connecting to the microgrid, and due to the lack of inertia inside the microgrid, the control of the frequency is very different. So we are now looking at that aspect, and a number of my students are looking at that. So the low inertia system that is in the microgrid and the behavior of the V/F controller. So over there, machine learning techniques are being utilized to assist in this low inertia system.
Very interesting. Thank you, Professor. We appreciate this presentation. It's insightful, and it's amazing to be with your kind self, sir.
Okay, there is a question from Lalita Savin. How the function of the static switch at the point of common coupling is controlled for faults in the microgrid? Is the microgrid island from main grid? Yes, the islanded mode of operation, you are separated from the grid. So the switch, the fast transfer switch, has two roles. One, when there is a disturbance, is to disconnect the microgrid from the main grid. That has to be done quickly to minimize any kind of damage to the equipment. The second function of the FTS is to reconnect to the grid. The microgrid has to be reconnected to the grid. At that point, you have to synchronize, and you have to make sure that the voltage on the grid and the voltage from the microgrid are at the same frequency, at the same voltage, so that you minimize the disturbance when you reconnect. And that has to be monitored, and again, the phase lock loops that are required to make sure that the synchronization takes place effectively, that is the role of the fast transfer switch. But now remember that the fast transfer switch has its own delays. It's an electronic switch, or is it a mechanical switch? So if you use a mechanical switch, there are delays in there. If you use an electronic switch, then there are still some milliseconds of delays. So even if the phase lock loop tells you to synchronize, the actual synchronization and the closing of the switch, there may be a time delay in there. And this is where I come back to this seamless, what they call the seamless mode of operation between these. It's not an instantaneous switch. There are time delays in there. And you have to look at that. Okay. I hope I've been able to give you some more information on that. There is another question from Raja Kumar. How do you determine the remaining useful life of the battery pack? A very interesting question. Thank you very much for the question. The useful life of the battery pack is something that Panasonic is very much interested in. Even the manufacturers themselves are not able to determine completely what is the remaining useful life of the battery pack. It all depends on the charge, the number of cycles, how quickly you charge and how quickly you discharge the battery packs. Now, this is going to take some time to be able to answer. We want to answer this question ourselves. We are not able to answer it right now. This is under investigation because now we want to look at the life of the battery pack over a number of years as it goes through this cycling. And then only we will be able to predict what is the remaining useful life of the battery pack. Okay, this is something that the manufacturer is very much interested in finding out. Okay. Any other questions?
There is one more question in the chat box itself, sir. Is any method adopted for detection of islanding? They have asked the same participant.
Okay. Well, at the moment, we only use the passive method of islanding detection, but they are in the literature. If you look in the literature, there are many other different methods. This morning, there was a presentation that you saw, and there are other methods. And I hope my research team will be able to look at different methods for detection of islanding. We are investigating right now. Like I said, we only have the passive method, but other methods is part of the research work now that, and we hope to report on that in the future sometime.
Thank you. Professor Sood, this is Imad again. I've asked 2 questions. Will you allow me to ask the 3rd question?
You have to ask Dr. Hari Kumar. Hari, he's the convener.
Professor Omhari, will you allow me, please?
Yes, one more you can ask, no problem.
Thank you, Professor. Professor, about the MPPT algorithm.
Yes.
Which has been used and simulated. We've noticed that it did not take into the consideration the shadowing or partially shadowing. Is that right?
Yes. Again, these are research topics. Implementing a microgrid is one thing. Doing a research project is another thing. So these are two different aspects. Our mandate in the beginning from the government was to incorporate a microgrid into our campus.
Excellent.
All right. At that point, we were required to deal with manufacturers, and the manufacturer that we had for this case was GE, General Electric. And one of the problems when you deal with the manufacturer, when you ask them this kind of specific question, what is the MPPT method that you're using? The details are not provided.
Okay.
That is commercial information, and therefore we are not able to share that information with you.
Okay.
So now you see our position as a research faculty, and you asked that question very specifically. We want to be able to answer that question ourselves, and we have methods. My student Haytham has looked at a method using a Kalman filter.
Okay.
To answer this question of shading. So that is a separate research project that some of my students are working on. But they have not been implemented in the microgrid. They cannot be, because right now this is a turnkey project that we have taken over. All right, and it is a functioning, living laboratory right now. I don't have access to the microgrid at any time of the day. I can only go and experiment at midnight when nobody else is using the system, because I cannot take the risk.
You understand, Professor.
All right, so this is, retrofitting. If it's a research lab where you have control of all these aspects, and you can change your algorithm and you can change your, that is a different ballgame. This is a practical installation where I do not have the luxury of being able to go and play around with algorithms, because now I have to supply energy to the campus and I cannot disrupt the operation of the campus.
Thank you very much, Professor.
Yeah.
Thank you very much, Professor, for being so open and honest with us. Thank you very much. We appreciate this openness.
Yeah.
Okay, so I think it's already 6:46 as per Indian Standard Time. So we are not able to take any more questions. I think participants can directly write to Professor Sood. We shared his email. Okay, if you have any specific questions related to the talk. I would now request Shelly. Are you there?
Thank you very much, Dr. Gupta.
Thank you so much, sir. It was really very informative, and I think most of the participants do think so as well.
Thank you, Professor.
Okay. I would request Shelly to please, for vote of thanks, please. Shelly, yes.
Thank you, sir, for enriching us with your valuable knowledge and esteemed presence. Also, I would like to thank all the participants Now with this, the session is over. We will meet tomorrow for the Expert Talk 12 at sharp 2:30 p.m. IST.
Thank you, sir. Thank you so much for finding
you very
time
much.
out of your busy schedule. And it is already, I think, we disturbed you early in the morning, sir. Sorry for
My
that.
pleasure. It was my pleasure. Thank you very much for inviting me. I look forward to further interactions.
Sure,
Thank you,
sir.
everybody.
Sure. Thank you so much, sir. Thank you.
Thank you, Professor. Thank you.
Thank you. I'll just share the feedback form, right? Okay.